This is section 7.5. We're still dealing with Laplace transforms. And today we're going to be talking about solving initial value problems. So this is how we can use the Laplace transform to solve initial value problems. So the first thing we'll do, kind of like taking the derivative or the integral of both sides, we're going to take the Laplace transform of both sides of an equation. Then we're going to use all of our properties that we know about the Laplace transform, its linearity, some things we know about integration and derivatives. And then we are going to look for the solution by looking it up in one of our tables or by using a suitable method like partial fractions to simplify it first and then resorting to the table. So let's look at how this can be applied. We're going to look at the differential equation y double prime plus y prime minus 2y is equal to 8t e to the t. And this is an initial value problem. So we've been provided with a couple initial values. Y of 0 equals 0 and y prime of 0 equals 3. So step one is to take the Laplace transform on both sides. So that's what we've done. And then we're going to start using our rules. So we start with linearity. We can break up these sums and differences into their own Laplace transforms. But then we're going to use our rule for derivatives. So the second derivative of y, when we take the Laplace of that, it's s squared times the Laplace of y minus s times y0 minus y prime of 0. And then we have a similar thing for y prime, where it's just s times the Laplace of y minus y of 0. Here, all we're going to do is factor at that minus 2. That comes down here. And then on the right, we're going to factor at that 8. So there it is right there. Now we're going to cancel out whatever cancels out. We're going to group like terms and such. So y of 0 was equal to 0. So both of these are just going to disappear. However, y prime of 0 is equal to 3. So that comes down as minus 3. We know from before that the Laplace transform of t e to the t is 1 over s minus 1 squared. Now we'll just stop for a second and explain why that is. We recall, or also we can look at the table to see, that the Laplace transform of t is 1 over s squared. But this e to the t, when you see something in the form e to the at, that a term tells you how much to shift it by, how much to translate it by. So since a in this instance, in this instance, a is just 1. It's just e to the power of 1t. We are going to translate it by 1. So it becomes s minus 1 squared instead of s squared. Now we're going to move this 3 over to the other side of the equation so that we now only have terms with the Laplace of y on the left, and then we're going to factor out that common Laplace of y. So we have Laplace of y almost isolated, but the next step is we need to find a common denominator over here. So we do that, multiplying 3 by s minus 1 squared. Well, s minus 1 squared is equal to s squared minus 2s plus 1. So multiply that by 3, you get 3s squared minus 6s plus 3. That's what we've added in here. So then finally, our goal is to isolate this Laplacian of y so we can solve for it. We need to divide both sides by s squared plus s minus 2. So that comes down here, dividing both sides by it. And now we're going to factorize that because s squared plus s minus 2 we want to find two values that will multiply to give us -2 and add to give us +1. So that's going to be s plus 2 times s minus 1. So that's how that factorizes. And then we can group together the s minus 1 terms because there was already an s minus 1 squared, so that becomes s minus 1 cubed now. And now we can step into our partial fractions. So we have a over s minus 1 plus b over s minus 2 squared plus c over s minus 1 cubed plus d over s plus 2. We'll leave this as an exercise. But what you'll notice is, since these values that we're going to solve for are just going to be real numbers, there's not going to be any t's or s's or anything in there. What we're going to be left with is a times 1 over s minus 1. Well, we know that when you take the Laplace inverse of that, you're going to get just a. And we know the Laplace inverse of 1 over s minus 1 squared, that's just going to give you t times b. This s minus 1 cubed, we're going to find out later, that's going to look like 2 over, sorry, not 2 over, that's a mistake. I believe you're going to find that to be t squared over 2. But you can prove that yourself using our original definition of the Laplacian transform. And 1 over s plus 2. Of course, these are all translated. So it's not just going to be a, it's going to be a to the e to the 1t. And this isn't just going to be b times t, it's going to be bt times e to the 1t, because this isn't just 1 over s, it's translated by 1. It's translated by 1. And this one is also translated by 1. But when we look at this s plus 2, it's translated by negative 2. So this is going to be e to the negative 2t times d. So you're going to notice something like this for your 4 solutions. Okay, next. Let's do it all again. Let's solve this initial value problem. Y double prime minus y is equal to e to the negative t, y of 0 equals 0, and y prime of 0 equals 0. So we'll take the Laplacian of both sides, and then we'll break it up using our linearity. And we know that the Laplacian of y double prime, well, it follows the same rules as before. It's s squared times the Laplacian of y minus, then we get y of 0 times s minus y prime of 0. In this instance, they're both 0, so they're both going to cancel out. So we're just left with s squared times the Laplacian of y minus the Laplacian of y is equal to 1 over s plus 1. Well, that left side is going to factor s squared minus 1 times the Laplacian of y. And then when we divide both sides by it, well, s squared minus 1 is equal to s plus 1 times s minus 1. So that's how we reach this form. And now we're going to do partial fractions. And we will go through the steps since this will be a little shorter than the other one. We want a and b and c. We want them all in the numerator, but we need to have a common denominator. And that common denominator is going to be s plus 1 squared times s minus 1. So a over s plus 1 needs to be multiplied by s plus 1 times s minus 1. So that's how we get this. B is already over s plus 1 squared, so it's only missing one factor. So that's s minus 1. So b must be multiplied by s minus 1. And c is only over s minus 1, so it needs to be multiplied by s plus 1 twice. So that's where we get the c s plus 1 squared. We expand, and we put them together based on what they're multiplied by. So 1 is not multiplied by s or s squared. So we're going to take all the constant terms and group them together into the first equation. Now there are 0 s's on the left. So this is our things multiplied by s, the s coefficients. And there are 0 s squareds on the left as well. So that's where we get the s squared coefficients, a plus c. Solve, 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 and we get our values. C is 1 over 4, B is negative 1/2, and A is negative 1 over 4. So we're going to plug those back in to this equation. There we go. Now, we know that this is all equal to the Laplacian of y. So we're going to perform the inverse Laplace of the right side of this equation. And again, as we said before, when you see this s plus 1, s minus 1 in the denominator, well, we can look at our table and know what the answer would be if it was 1 over s. For instance, the inverse Laplace of 1 over s is just 1. The inverse Laplace of 1 over s squared is t. But when you have to translate it by plus 1, that means you're going to put a negative 1 in the power of an e. So it becomes e to the negative t times whatever other value you would have. 1 over s just becomes 1. 1 over s squared becomes t. Over here, we have 1 over s minus 1. So s minus 1 translates to a positive 1 power of e. And again, it's just multiplied by 1. So this is our solution. For our final example, we're going to solve the initial value problem, y double prime plus ty minus 2y equals 2, with the initial values y of 0 equals 0 and y prime of 0 equals 0. For this problem, we are going to need to make use of the theorem from section 7.3. And that's how we're going to deal with this t factor on the y term. So when we have to solve for the Laplacian of ty prime, it's equal to the negative derivative of the Laplacian of y prime. So we'll see when we get there. But we'll start as normal. We will take the Laplacian of both sides and start breaking it up using our linearity. We know what the Laplacian of y double prime is by now. And this y0 and y prime of 0 term, they're just equal to 0 in this instance, so they'll cancel out nicely. Now, here we have to take the inverse we have to take the Laplacian of ty prime. And as we just stated from our theorem, that is negative derivative of the Laplacian of y prime. And then on the right side of the equation, we can just solve because we know the Laplacian of 2 is just 2 times 1 over s, or 2 over s. So we cancel out these zeros and we're left with s squared Laplacian of y minus the derivative of the Laplacian of y prime minus 2 times the Laplacian of y equals 2 over s. Now we need to figure out what this Laplacian of y prime equals. Well, that's an identity we've used already during this video. That is equal to s times the Laplacian of y minus y of 0, which is just 0. We are going to let y equal Laplacian of y, hopefully to just simplify things a little bit so we don't have to keep writing Laplacian of y over and over. So now we just have s squared of this big capital Y minus the derivative of sy minus 2y is equal to 2 over s. Now calculating this derivative is actually a product rule because s and y are both themselves functions. So the negative derivative of sy is this statement. Negative s times the derivative of y minus the derivative of s, which is 1 times y. Now we'll group like terms. So we move the derivative over here and we take all the y terms and we move them over here, keeping just 2 over s on the right. And this may start to look like something we're familiar with, especially after we divide both sides by negative s to get the dy ds all by itself, some function of s multiplied by y, and some function of s on the right side of the equation. This is a linear equation. So for linear equations, you find an integrating factor that is e to the power of whatever is multiplied by y, the integral of that. And now we will calculate that integral. And this will take a couple steps. So we'll actually explain where this comes from. So e to the power of the integral of negative s plus 3 over s ds. Well, that becomes e to the power of negative 1/2 s squared plus 3 ln s. But now this plus inside of a power means we can break them up. So it's e to the negative 1/2 s squared times e to the 3 ln s. Now we have e to the negative 1/2 s squared times e to the ln s cubed, because our law of logarithms say that 3 can come in as a power. And then finally, we have e to the ln of something, so that can just cancel out. So this s cubed comes all the way down as a factor. And we get s cubed times e to the negative 1/2 s squared. That's our integrating factor, so we're going to multiply it by both sides of this equation. And now the left side's starting to look very ugly, but we remember the reason we've done all this is so that the left side looks exactly like a power rule. So without any further thought, we know that the left side is, sorry, not a power rule, product rule. We know that the left side is the product rule evaluation of the derivative of this times this. So we can simplify it as such. And then we take the integral of both sides. The integral of a derivative just cancels them both out, so that's simple enough. But the right side, we need to actually calculate this integral. We're going to let u equal s squared. And then when we calculate what ds is equal to, lucky there's going to be a 2s in the denominator there that is going to cancel out with this 2s. So it simplifies very nicely as just the integral of e to the negative 1/2 u du. When we integrate that, this negative 1/2 by chain rule becomes a negative 2 out front. And then we replace u with what it's equal to, which is s squared. And don't forget your plus c. Now, we want to isolate this y, because even though we have a solution, we'd like to have an explicit solution. So we have to divide both sides by s cubed e to the negative 1/2 s squared. Now, in one instance, these things will cancel out very nicely. There's an e to the negative 1/2 1s squared here that will just cancel out perfectly with it. So it just becomes negative 2 over s cubed. But c isn't like that. So c becomes c times e to the 1/2 s squared divided by s cubed. Now we perform our substitution. Remember, y is actually equal to the Laplacian of little y. And this, it ends up, is just equal to negative t squared. Now, half of the reason for that is that this c e to the 1/2 s squared term, that must have c equal to 0. And the reason for that is that all Laplace transforms must go to 0 as s goes to infinity. And that can be found on page 379. You can see quite clearly that if s went to infinity in this term, it's going to go off to either positive or negative infinity, whatever c is. But since it has to go to 0 to be a Laplacian, it must be true that c is equal to 0. So if c is equal to 0, this whole thing cancels out, and we're left with negative 2 over s cubed. And I'll leave that as an exercise for you to show why the Laplacian of negative t squared is equal to negative 2 over s cubed.